Hello, everybody. My name is David Soldani, and I'd like to thank you so much for having me today at our Huawei YLab JSC workshop. I have been in the ICT field for more than 25 years, and 10 of those at Huawei, serving initially as the head of the Center Research Institute in Europe with Dr. Tong, and now I'm based in Australia, contributing as CTO and CSO at Huawei Australia, but also as the one of the ICT experts within the Asia Pacific region. My presentation on AI-enabled automation in future mobile networks consists of 3 parts. So first, review the main works ongoing within the standards. Then I'll show you some example of deployment scenarios, and the last part is about new research directions. So starting from the standards, the first contribution I'd like to introduce you is from the ENI. ENI stands for the Experimental Networked Intelligence group within the ETSI. What I've done is the definition of an architecture that uses the AI technology and a context-aware, metadata-driven policy to assist the ETSI Mano as illustrated in this figure. So we have a number of inputs and information taken from the different layer of the infrastructure, and out of this information, what we have is a new proposal on the next state or how to change the policies to the orchestrator. So the work includes both the type 1 hypervisor and type 2 hypervisor implementations, as well as the OS containers, which means in practice the share host OS kernel. And what ETSI has recently output are 5 possible options. Here, one of those is illustrated on how the container infrastructure service management and the container infrastructure service are mapped onto the NFV Mano architecture. The second work is about it's from the focus group on machine learning for future networks that includes 5G. It is from the ITU. What I've done is really comprehensive architecture and machine learning pipeline definition, and now they are licensed with the 3GPP so that those requirements are incorporated into the definition of future technical specification. In practice, what they do, they propose a machine learning pipeline that consists of a number of nodes. So we have source, a node that is responsible of gathering and generating the data. Then we have a collector that provides input to a preprocessor where data are sanitized, clean, and aggregated. And then we have a model. So the model is nothing else than an inference, a function that requires to be trained in a sandbox, as production data shall be never practically used. Then we have a policy node that for control mechanisms, so that the impact to the live network can minimize. We then have a distributor and a sync function, which is the target node of the machine learning output on which the actions are taking place. They also introduce a machine learning function orchestrator here, which translates intent, so the description of particular use cases, into placement and chaining of machine learning functions. It's based on a closed loop, and the measurements are practically used for the model selection. So the figure illustrates here the deployment on an end-to-end 5G system of 2 machine learning pipelines, and the target is to improve the quality of service end-to-end based on latency measurements within the radio access network, as well as latency extracted from tolerant applications residing within the application functions. They're also defining a number of use cases, and example of those are network slicing, how to improve the user plane performance, signaling, application, security, and so forth. 2GPP also in release 15 introduces an important data analytics function denoted as network data analytics function, and currently specified only for the core network. So it's a function basically that receive and extract data from the control plane network functions. There is also now an attempt to expand and introduce this functionality across the whole network, especially the radio access network. They define a number of use cases. Here I've listed some of them, and they range from load level and load analytics predictions down to how this function can be implemented for improving congestion situation or network load performance, looking at the specific network functions. And then, of course, we have a number of use cases on how the end user experience and quality service could be improved. Also, we have a lot of work done by the Oran Alliance, and I'd like to mention here because what they've done is they have introduced, looking at the RAN, radio access network itself, a number of many more interfaces compared to the open RANs currently specified in 2GPP. And here you have a list of the new interfaces, but in particular, what is relevant today is the introduction of 2 particular functions. So the non-real-time RAN intelligent controller and the near real-time intelligent controller placed in the control plane of the central unit and on the management plane of the radio access. So the Oran currently comes along with still many challenges, and in particular, I think it is relevant here to mention the challenge we're having on cybersecurity, because it expands threats and attack surface of the network, and the network security risks are especially linked to the lower layer split, the near real-time RAN intelligent controller, disaggregation of software and hardware, of course using cloud, and also due to the introduction of new interfaces, especially the O1, O2, and open fronthaul on the M plane, on the management plane. An interesting work has been recently published in the IEEE Communication magazine. It was a part of one of my special issues, which I thought here to mention, because what the target here, what they propose here, it is an end-to-end framework with standard functions from 2GPP, ETSI, and Oran, and the new AI-based algorithm, as illustrated in this figure. So basically, what they do, they propose this architecture and the new algorithm so that they can use all the current defined functions, which are basically two of them from the 2GPP. That's about the management data analytic functions that collects data at the network function level and network slicing level, and the network data analytic function, which practically it is a function, as I've explained earlier, of the control plane, the core network. And they're also making use of the radio network information base and run intelligent controller defined by the Oran Alliance. So here you see the architecture in high level and the new algorithm they introduce for long-term, mid-term, and short-term forecasts. And in particular, what they target here is to extract inputs from the already well-defined functionality within the management and orchestration domain and control plane by the 2GPP and Oran Alliance, and the output and then passed to the corresponding engines so that the virtual network function can be optimally placed, as well as resource appropriately scaled, and the PCF policy improved, as well as the algorithm performance. Algorithm meaning the radio resource management algorithm can be accordingly updated to maximize the radio interface performance. So here you have how the algorithm has been structured. We have an encoder and 3 decoders depending on the particular prediction function that has to be, that provides them inputs to the corresponding engines. It is based on the fact that they are considering the subsequent snapshots as of key performance indicator as maps, so they can use convolutional neural network for analyze the data and then pass them to other type of neural network for making the corresponding prediction. Huawei has done a lot of work on AI, and since 2018, Huawei has in place full stack AI strategy that addresses all possible scenarios. Today, already all products are available. So full stack means that it's already available at the chipset. So Ascend 310, Ascend 910 is already available for all products from wireless, from the access component to the optical router switching core and server. And on top of that, we have the chip enablement platform, so the computer architecture for neural network where on any kind of framework may run. So may have traditional frameworks such as TensorFlow, PyTorch, or even we may think of using a MindSport, that is the Huawei framework where our algorithm can be defined and trained. So for the training in particular, Huawei has created a market place denoted as Modelars. It is an application enablement platforms that run on the Huawei public cloud. So the looking at the network as an autonomous car. So what we're saying here is to have an autonomous driving network, we represent different level of autonomous networks as we have done for autonomous vehicles. And in this case, we see that today we are still really having in place a solution partially automated. So, and like the decisions and the service experience, and as well as the system complexity is still addressed by humans. So the target is by 2025, I would say even by 2030, is to achieve a full autonomous network where all possible tasks are handed over to machines. Of course, intended that some of the tasks will remain within the human control. It is particular when we want to have remote interventions if something goes wrong. So the way approach to autonomous network driving has been based on scenarios. So it's a scenario-oriented approach. And basically what we have done is we have taken the complete end-to-end business processes of our customers and segmented those into 4 parts. So we go from planning, design, deployment, to optimization and provisioning. And within those particular business processes, we have defined different scenarios. And for each of those scenarios, we have developed the corresponding solution. And on this slide, you have examples of where we are today and what we are thinking of addressing in the near future. Now, looking at specific use cases, I'd like to introduce you some of the results we have attained in the field using 5G, but also LTE systems. So the first is on network planning. And for network planning now, we do have an extensive approach for intelligence, traffic predictions, and the predictions are possible in a short time, as well as in considering much longer period, up to say 12 months of history data. So the approach, what I've seen and also contributed, has been based on LSTM, so recurrent neural networks, and I say that it works very well. So we use the first part of the data to train the model, and then we leave a buffer to validate the model itself before it is then introduced and for a real prediction of using fresh data received from the network. Then the other application is on network deployment, and we have already a number of solutions. For example, for reducing the number of parameters that needs to be optimized to plug and play type of solutions, not only thinking of hardware, but also software. And then, of course, the ultimate goal for us would be to achieve a zero interventions with seamless integrations of with the network management system. Another area of application I think extremely important is on troubleshooting. This is the case of the minimization of the mean time to solve a particular fault. So what our solution does, first using AI, is to reduce the number of alarms. Like in this case, alarms have been reduced to a factor 100. Then the solution and the algorithm, what it does, finds the root alarm based on our priority and random forest algorithm. Once the root alarm has been identified, we can easily solve all the problem using a hierarchical type of approach. And then about the performance optimization, I'd like to illustrate you the case of Massimino. So Massimino here, we have a solution that improves three key parameters, and that is about the azimuth, the width, and the transmission power. And our algorithm shows, or the experimental results show that the efficiency was improved of a factor 10, and the downlink average user throughput improvement was of 2 digits. Then on network provisioning, I think the main application has been on energy saving. And our strategy was to follow the 0-bit, 0-watt approach. That means wherever we don't have traffic in place, we should not have power dissipation. So that algorithm was applied and to 4G systems. And as you can see on this figure, what we have done is to divert the traffic to other nodes with an already ongoing communications, and then we managed to shut down transmissions where basically there is no traffic. So if that is basically what is available today, looking at the 2025 and beyond, we have four main high-level targets for our mobile communication system. And the first one is to achieve superconnectivity. It is a superconnectivity that you can see here, or what it means in practice in terms of bit rates within the access network aggregation and backbone network. We need to have a system which meets the requirements of adaptive elasticity, and here I'm thinking of an end-to-end network slicing concept, meeting different type of SLA requirements, especially for vertical sectors. We need to have a convergent system that's basically is already achieved with the introduction of the 5GC, but I think extremely important is to have intelligence synergies across all network domains. As you can see on this figure, the artificial intelligence is expected to be applied across all network vertically and horizontally, considering the different type of protocol stacks. And in terms of roadmap, we are expecting that the artificial intelligence will gradually replace the human intelligence for autonomous network operations, and this is practically the target by 2030. As you can see already today, that the traditional OEM approaches have reached a ceiling, and now basically automatic system intelligence is expected to grow and really help us finally to achieve an autonomous network with extremely limited human intervention. So looking at the possible research direction on artificial intelligence and machine learning, I've just listed here a few of them, which I think are extremely important. So I think the traffic steering, traffic prediction, remains very extremely important. So we need to think of different type of scenarios and the different objectives as the network will be virtualized, and quality of service and quality of user experience are also important to be addressed, because we will have the deployment of new service applications. I'm thinking of massive AR, VR, but also an holographic rendering by 2030 with different type of characteristics model. And a lot of research has to be done in this area as well. Then we have massive MIMO, they will evolve. So as you know, it's going to be announced in release 16 and 17. So we will have different distributed PAN systems, coordinated actions, and many important problems, cell-centric quality service, quality user experience in multi-cell are example of those. Slice optimization, so that make it simple and ensure that the service level agreement and corresponding requirements are met, especially in the radio access network. And then with introduction of the V2X communication, it is extremely important to have a context-based dynamic optimization of and others. And also I'm thinking of the connectivity to unmanned aerial vehicles, and or in general any kind of robotic platforms. We need to find a way to optimize the resources provided to those platforms based on a number of measurements, I think especially from the devices, but also understand the flight path or the path that particular object is expected to take. Energy savings will be there, so we want to be greener and reduce the greenhouse gas emissions. And also, you know that 20 to 40% of the OPEX in carrier networks are linked to energy consumption, and 2 to 3% and reach out 2 to 3% of the world energy. And the last but not least, I think it is extremely important to focus on AI, machine learning, security. We do need a new architecture, security by design, new controls, augmented by a zero trust model. So with this, I'd like to end my presentation. I hope it will inspire you and help you define and position your new research direction. Thank you so much, and goodbye.